to 1992 to 1994, from 1994 to 1996. And you can see on the bottom of this chart, you can see where each one of the lines is perpendicular to the line that I just made, and it is at the even points that I just referred to. So the first trapezoid that we're going to do would be this first one, and it would be from 1990 to 1992. So we look at that at the chart, and we see that at 1990 it's 4.9. So without our 1/2 and without our width, which is 2, it will be 4.9 plus 4.6. There we go. That is our first trapezoid. And really, like we were talking about earlier, it's times 1, because 1/2 times 2. But that's irrelevant. So for our next trapezoid, all we're doing is adding these up, because we're eventually going to find the area underneath the function. And so for our next, we have, from 1992 to 1994, 4.6 plus 4.3. And if you might have noticed, these two are the same. And that is because once you go down the list, what the height 2 was previously, that becomes the height 1, because they're all touching each other. So we want that. So there's no room for error in between these. So this here is height 2, and this is height 1. So it's quite simple. We're just doing that throughout every single trapezoid, and once we get to the bottom, we add them all up, and each one of these segments up. And now I'm going to do that, and I'll give you an answer in just a second. So I added each of the trapezoids up, each of the areas of the trapezoids, respectively, and I came out with this. The answer to the integration problem and the area underneath the formula is, oh, didn't see that one coming, is is 73.4 units squared. So this is our answer. This is how much area is underneath the entire formula from 1990 to 2010 with 10 subdivisions. So all this area. So as you can see, it's much more accurate than a solely left-bound Riemann sum, or solely a right-bound, or even a midpoint Riemann sum, because it's the average of them, so it comes out to a much closer value. And it's really a useful tool with information like this, where the data itself is scattered and not necessarily consistent with one consistent slope throughout each point. So the next thing that we want to do is we're going to quickly find the rate of change, the average rate of change of the whole entire function. And this is quite easy. We learned this early in our math career, and it's just we're finding the slope of the entire function. So what we do is we use our little formula, which is the change of y divided by the change of x. It's a little sloppy, but I'm used to that at this point. And so we go to our data, and we go to 4.9, so 1990, our first point, and then our last point, which is at 2009, and we go to our y values. So there's 4.9 and there's 3. And we see that in our chart. We can see that it goes all the way up. It starts at 4.9 and it ends down at around 3. And so we're going to, oh, I'm sorry, actually at 2.9, because we're ending at 2010. So, wow. Okay, so we're going to do this out. So that equals 4.9 minus 2.9. I'm going going to come out to a nice even 2, divided by our sort chain of x. So where are we doing this graph from? What are the extremities of the graph? It's from 1990 to 2010, so that's 1990 or 2010 minus 1990. And now this equals 2 over 20, which equals 1. Oh, jeez. Sorry for the technical difficulties that I've had this entire time, which equals 1 over 10. And I'm just going to say out this last point because it's not going to write well. Which 1 over 10 is the slope, so that in the function it would be x over 10, and that is our slope. So you can see this slope looks like it's about 1/10. It moved down from around 5 to down around 3 in 10 different subdivisions. Therefore, it went 5 subdivisions, therefore it went at about the slope of 1/10. So it makes sense. It's a great method, the trapezoid approximation itself. With it, you can find many different things. The integration itself is made much easier, and with that integration, you can come out with a whole understanding of the graph itself. In this case, it's sort of vague, but 73.4 units is really the number of beds per 1,000 people over the 20-year span. So it's not totally sensible in this specific lens, in this situation with the hospital beds, but in any other situation it represents a similar thing. If we had this graph representing the money in the bank, the money per $1,000, so $4,900 down to so $4,900 down to $2,900. If this was a depleting value, then it would be the integration of it would be the amount of money that you had the entire time. It would be the total amount. So if at each interval you withdrew the money and put in that same amount of money for it to be depleted again, and did that continuously, that integration would be the value that you had in total. I hope that you learned something. Thank you for watching. Now, in terms of the actual topic itself, it's very interesting that the number of hospital beds has declined so much. I've looked into it, and it corresponds with the amount of research being done. The amount of research being done has increased over the past 20 years. Therefore, medical technologies and advancements have increased as well. So that's directly proportional, the amount of research to the amount of to the actual advancement, and inversely proportional to that is the amount of hospital beds, as we see as the number of hospital beds declines. And that's another factor in this is population growth. So as the number of people increases, the number of hospital beds per set group of people, per 1,000 people in this case, declines as well. So with this information, with this project done, I predict that within the next 100 years as well, or hopefully sooner than that, as hospital service steadily declines, as population increases, and as medical technologies increase, because these technologies won't be able to be applied in mass numbers, since the facilities in which they're supposed to be used aren't carrying as many people, or don't have the capacity to carry as many people. I see awareness in the future. The government will take control of this, hopefully, and advance along with the technology the capacity of hospitals to take in these numbers of people. I found this a really interesting project, and I hope that you did as well. Thank you.